Okay, hello everybody to another episode of JUXTCast with me, Malcolm Sparks. James Henderson here.
Hi there.
James is our head of engineering at XDDB, and JUXTCast regular Jeremy Taylor.
Hey, I look after XDDB and our products at Jux.
And really, really excited to have a special guest on this special episode of JUXTCast. We've got Nathan Marz.
Yeah, great to be here. Thanks for having me.
Yeah, hi, Nathan. Nathan was one of the Clojure library authors that I first heard of when I first got into Clojure. We were doing some work with a library called Cascalog. Actually, James, you were using Cascalog on a client site, weren't you?
It was actually the company I worked for at the time. Yes. Yeah. So we used it for our overnight batch analytics. We were pulling quite a lot of data down from the social networks and using Cascalog for a lot of the graph algorithms to figure out what content would resonate with certain audiences.
And I remember Cascalog to be a data log running on Hadoop. And then the following project, I think, was Storm, because my first project at Juxt, I was building a Storm topology and kind of beginning to learn about data flow. And that was eons ago now, right? So you must have been doing this for a long time, Nathan. So just like to touch upon, what's your story? What brought you to programming, and particularly with Clojure? How did you discover Clojure so early on? And what was the background to that?
I started programming when I was 10 years old. My very first exposure was actually my brother. My brother's 6.5 years older than me. He was taking a computer science course in high school, and they were doing QBasic, and he showed me like at home, like what they were doing. I thought it was really cool. I don't remember exactly what it was, but you'd write like a small program and then the result would be like a line graph or bar graph. And I was just really fascinated by it. And my brother, he loved that I liked it because I ended up doing a lot of his homework for that class. That was my first exposure. From there, I discovered that you could program graphic calculators. I don't know if you guys remember. You guys remember like the TI? Yeah, TI calculators. I had a TI-82. I had a very simple programming language on it. And that's really how I learned to program, was on that little keyboard. I spent so much time with that thing from like age 10 to like age 17. That was like my primary programming platform, just making games. I remember when I graduated from the TI-82 to the TI-89, one of the mind-blowing things for me was just on the TI-82, the only variables allowed were just the letters A through Z. Like you couldn't have multiple characters in your variable, but the TI-89 you could, and that was like incredible for me. Because when you only have 26 variables to work with, yeah, it was tricky. So that's how I got started. And then I moved on to C++ in high school, and then in college learned Java and stuff like that. I first got interested in Lisp from Paul Graham. This was like before he started YC, but he was writing about all sorts of topics on his blog, including one article that's really famous about how he did his startup via web with Lisp and how it just gave them such an advantage, how they were able to iterate so fast and stay ahead of their competitors. I thought that was really interesting. And just like the concepts, I didn't really understand it at the time, but the concepts of like macros enabling you to do something you can't do in other languages just sounded really compelling to me. I guess I somehow understood that at an intuitive level, even if I didn't actually understand specifically. I always had that in the back of my mind. And then I was working for a startup, my first job out of college, just doing Java. And then I heard about Clojure on the JVM. So it would have been completely compatible with what we were doing. And that was just really interesting to me. I had done a project at that company where I also knew about Datalog from college courses. And I thought that would be a really interesting way to do MapReduce. And I did a hack project where I literally implemented like Datalog, like with Alexa and Parser, and had to compile it's compiling to cascading, which then compiles to MapReduce. Right. Cascading was this Java library for doing like data flow on top of MapReduce. I was able to get like a basic prototype of that working within one day, but very quickly I realized that doing it as its own custom Datalog language there was just a lot of inherent complexity there, because you need to be able to plug in custom logic, custom operations, and having to like make a custom registration system was a mess. So then that was my first motivation for Clojure, was to build a Datalog thing, but in Clojure, so that you don't have any of this complexity, so that you're just able to use just regular programming practices to do stuff like that, to express your like custom operations. So my first project in Clojure was actually, Cascalog wasn't actually my first project. My first project was just a smaller project just to get the basics. I don't remember what it was. It was some sort of queuing system. or like helper for like batching queuing. My second project was Cascalog, and then which was actually a pretty, I guess, ambitious project for your first thing you're doing in Lisp, just because like I was using macros and like all the like more advanced stuff like straight off the bat. I think the Cascalog implementation, like that first project I did, if I look back on it, I didn't know what the hell I was doing. I would implement it completely differently today, but it turned out to be a very beautiful, elegant API. And one of the things I discovered from that was I didn't just want to do like custom operations that I plug into your data log flows. It was also very useful to be able to write functions that generate Cascalog queries dynamically. It's just the power of abstraction and composition. And from there, I was off to the races when I was able to make just a project that was so useful doing something that you couldn't do that elegantly in really any other language. And then Clojure became my primary language from there. And then after that was my next big project was Storm, at least my next big open source project was Storm. And that was, I did Storm in 2010. So that was a long time ago.
So that got you onto the road of Storm. And there are obviously some things that was perhaps a stepping stone towards Rama. And there were things that you took from Storm, or at least the data flow between nodes. And certainly I recognize reading about Rama, the importance of just making sure that you have that reliability. I know in Storm had a capability of guaranteeing that it would count all the messages that came in and could guarantee that the number of messages received were the number of messages that were sent out. That was I think it was some kind of bit mask that you used to just guarantee that. And so that if that wasn't true, you knew you didn't have enough messages and therefore your calculation was potentially wrong. So I guess some of that has made it to more probably the distributed part of Rama. Do you want to touch on that and introduce, how did you go from Storm to Rama, or did you have other projects in between? And what was the time, what was the motivation that made you think, right, I need to spend 10 years building something cool?
Yeah. So I did Storm in 2010, released it in 2011, or open sourced it in 2011. I started working on Rama in 2013. There's a few key things that happened from 2011 to 2013, which led me to commit to Rama for 10 years. So the first thing is that Storm becoming such a big open source project, so widely used all over the world. Not only was I using Storm for my own use cases, which was first at the startup Backtype, and then we were acquired by Twitter. So then at Twitter, and there were lots of use cases Storm was applied for at Twitter, kind of all over the spectrum. But also I was helping the open source users with their use cases, which were also all over the place. So I had a lot of exposure to just every use case imaginable for doing data processing, especially at scale. And so I became very familiar with just the ins and outs and the issues you deal with of building applications at scale. So all that work led me to writing my book, which was about, I came up with the term Lambda architecture, but my book was about stepping back and thinking about building backend systems from first principles, because that actually had never been defined before. A lot of people consider like the relational database the gold standard of backend systems. But let's say I just pose the question to you, does a relational database capture all possible backend systems you'd want to build? Right? And then you think about it and you're like, okay, the model, you have tables and you have primary keys and you have foreign keys and you have relations and you have SQL language. And there's not a direct connection between that and then does that capture all applications? You actually can't say that. It's very unclear. And in my book, I defined what those first principles are. What's the actual starting point if you actually want to think about a general purpose way to build applications at scale, which is basically what Rama is. Rama derives from those first principles. And the first principle is extraordinarily simple. So all a backend does is it answers questions, right? The goal of backend is to answer questions on information the backend has seen in its entire history. And the most general possible way you can formulate a question is as a function of all the data you've ever received. Okay, query equals function of all data. So that clearly encapsulates everything you could ever possibly want to do with a backend. Anything you would want to compute, you can compute as a function that literally can look at all of your data at once, right? That's obvious. Now, obviously, that's not practical, but that's besides the point, right? The point is, what is a starting point that we can begin to think about this? And then from there, what are the trade-offs we have to do to actually make it practical? And then start to think of a general purpose system. And actually, you only have to make one trade-off, one modification to that, which is to introduce the concept of an index. So instead of query equals function of all data, you have indexes equals function of data and query equals function of indexes. So that actually is practical. And actually every backend that's ever been built is an instance of that model, even though they haven't been thinking about it like that, right? And usually you're using different tools for every piece of this. You use relational database plus Elasticsearch plus maybe other databases too for the indexing part. You use maybe Storm plus your API server plus custom workers for the function of data part to compute your indexes, and then maybe use another system altogether for doing your queries. And the motivation to thinking from first principles is just that, just the cost of building these systems, both all my use cases at Twitter and also all the use cases I was working at, helping people through my open source work, it just felt so wrong because we work in a field of engineering, which is entirely about abstraction, automation, and reuse. So it seems like the work you should be doing for an application should just be whatever is unique to the application. We should be able to reuse the rest. But with backend development, it didn't feel like that at all, right? And one example I like to use, and you could say this about any application, but I use Twitter as an example just because I work there and I'm very familiar with the implementation. But the Twitter product, the consumer Twitter product, you can describe that in all of its detail in terms of what it does. You have accounts and profiles and follows and timelines and search and an API. You can go through every last detail of that in a few hours, right? It took Twitter 200 person years to build that at scale. So how can that be in a field that's entirely about abstraction, automation, and reuse? It takes 200 person years to build something you can describe in a few hours. So that really bothered me. So that's why I was very interested in finding a way to enable abstraction, automation, and reuse where it had basically been non-existent, effectively non-existent, given just the extreme cost difference between how long it takes to describe an application versus how long it takes to build it, especially at scale. I think this is still true even when you're not at scale, but it really gets crazy when you're at scale.
There was a paper in the 1960s that was very similar. Somebody made the observation that why does every project seem to be something you can describe in one page, but still costs $1 million, and that was in the 60s, $1 million to build. And that sense of sort of complexity and what's going wrong, and that kind of why is it like that? That question has been asked for decades now, and it's still being every generation asks that question, and we haven't come up with good enough answers clearly because every generation asks that question.
Yeah, that's true. And I wish that every programmer was asking themselves that because there's something deeply wrong. So Rama is basically, in my book, I showed, using from these first principles, query equals function of all data becomes indexes equals function of data, query equals function of indexes, right? This is something practical. And I showed how you can do this in a general purpose way, but using existing tooling. So still by combining lots of tooling together. And one of the things I had to do in my book repeatedly is say, you want to be able to do stuff this way, but the tools only support it this way, right? Like databases can only do these indexing models. So you're limited by that. But I'll show you how to do it anyway. But I made it very clear, you're constantly having to twist your application to fit your tooling because every tool that exists, it's very specific. It's very narrow. Databases are one particular data model. Computation systems are one particular way of doing computation and one particular way of doing fault tolerance and so on, right? And just go on and on with all the different tools that people use. And in 2013, when I started working on Rama, I understood that I didn't know exactly how to solve it, how to build a general purpose system for that programming model of those first principles, but I had the broad outline. So the things I understood at that point was, besides the programming model, I also understood that the right way to represent an index was as data structures, not as these magical specific data models. And that actually any data model can be expressed as data structures, right? So you look at key value, that's just a map or distributed map. You look at a document database, that's a map of maps. You look at a column-oriented database, that's a map of sorted maps. A graph database would be a map of sets, or it could be multiple indexes to represent a graph, like one for the node properties, another one for the adjacency list, with some possible variation if you want to store properties on the edges, so on and so on, right? Any data model. But if you're representing it as data structures, then not only can you do those data models, you can do infinitely more, right? And I understood that building an application at scale involves materializing multiple indexes, and you want to shape those specific to the use cases you want to support.
To what extent do you think Clojure had some influence on your thinking there? Because you talk about in the introduction to Rama about every data structure is really, it's either a map, like a key value store, or it's a map of maps, or if it's a document store, or it's a collection. And in Clojure, as opposed to coming from object orientation, the first thing you're faced with is that everything in Clojure is either a map or a collection, or a map of collections, or a collection of maps, or a nested kind of composition of those things. And those are everywhere, and they're all public, and they're all first class, and you can introspect the whole thing. And so it very much kind of inside a Clojure program, you're exposed to this idea that data structures are at their very heart very simple things.
Mm-hmm. Yeah, I think it definitely was an influence. I was programming Clojure full-time for 3 years, a little bit more than 3 years before I started working on Rama. I definitely understood the value of it, and almost certainly, I wouldn't say I explicitly thought, oh, let me take this thing from Clojure and apply it towards big data. But certainly it had become very intuitive for me by that point that I understood just the value of data structures. And it just became very obvious to me that data models were just data structures. And another thing that Clojure exposed me to was just like composable abstractions, right? Which Clojure and Lisp programmers are going to understand much more intuitively than other programmers in general, because that's just such a common thing to do. And so expressing your indexes as combinations of data structures is one form of composable abstraction. And Rama's full of those, where you achieve power through composition of simpler primitives rather than have to build these things specifically over and over. Like when you look at, again, I use Twitter as an example, but again, it's true of pretty much every big company. Twitter had to build multiple databases from scratch because the existing ones didn't meet their needs, right? And the databases they're building are really just variants in some respect, different data model, or it's in memory versus not in memory. And then they have to redo all the work of partitioning and networking and replication and process management that is already done by all the other databases they're using. And if you can express your databases as the composition of simpler primitives, now you do have abstraction, automation, and reuse, because you can express through composition and you get all the other stuff is already taken care of for you. So that's like a big deal, like a really big deal.
And I'm guessing it was far easier to turn those data structures into a distributed system than it would have been if you were trying to replicate, for example, an entire database as that same distributed system at scale. Like the fact that you've got maps and collections, and that the task is distributing those rather than the task of distributing the whole database.
With distribution, there's just a lot more that you have to deal with. So the stuff that Rama is able to do generically is one is partitioning, right? When your data structure is distributed, you have to decide how do you actually partition it. On which partition are you going to add a new follower to someone? And what you deploy in Rama is called a module, right? And module has partitions. You have 64 partitions across, let's say, 64 nodes. All right, on which partition are you going to add that follower to? And that's one of the things you have as part of the design of your application is how you partition your indexes. And you have complete control over that with Rama. So besides the actual data structures you're using, you also control your partitioning. The other thing that Rama implements for you, which is very important, is replication. So incremental replication, so that if you lose a node, which is 100% guaranteed eventually, especially when you're running at scale, the higher scale you're running at, the more frequent that occurrence will be. If you lose a node, then there has to be something ready to take over immediately. And if you want to build applications, most applications need strong guarantees of visibility, right? So what Rama guarantees is that any information visible on a leader is also going to be visible on all future leaders. That's the basic guarantee you want from replication. Actually, incredibly difficult to achieve. I don't think we spend more time on anything in the Rama implementation than replication. It was insanely difficult, like very humbling building replication from scratch, especially with Rama being such a generic system with so many different things it's doing. And these things have different like SLAs associated with them. Some things are okay with taking a few hundred milliseconds or even seconds, whereas other things need to be done within 2 milliseconds. Supporting all those within one system, all sharing the same replication system was very difficult. So we had to innovate a lot in replication because nothing had ever done heterogeneous replication like this before. Other systems like Kafka, you're always replicating the same thing, log entries, and all the log entries are going to be about the same size. So that was like a major thing we had to figure out. And so like when you are able to express your indexes as a composition of simple primitives and you get all this stuff done generically for you, now you're just you're in a much better place when it comes to building applications, especially at scale.
Yeah,
Maybe we should actually introduce what Rama is. I think we might have skipped over that.
Shall we talk about that? I'd love to know how you know that your fault tolerance and robustness has achieved those guarantees you talk about. How do you guarantee that those guarantees are something you can offer? But before we do that, let's just touch upon, we've talked about Rama being a kind of composition of data structures. That's what we know at the moment. What else is it?
Yeah. Okay. So just in terms of what Rama is broadly, so Rama is a programming platform that's capable of building entire backends with very diverse computation and storage needs end to end, including deployment and monitoring. And it's massively scalable, just inherently massively scalable and completely fault tolerant. So whereas building backends now and basically for the past 50 years has involved combining together many tools, sometimes dozens and sometimes more. Even at low scale, you're oftentimes combining many tools together. Rama is able to do everything, both computation and storage, on one platform. So one way to think about Rama is as a programmable data store on steroids, where you mold your data store to fit your domain rather than twist your domain to fit your data store, as is the case now. And I talked about the first principles of indexes are a function of your data and queries a function of your indexes. And that's the flow of what it looks like to build an application on top of Rama. So you have data just comes into Rama on what's called a depot. So a depot is just a distributed append-only log of data. Then you build these things called ETLs. So that's the function of your data. So it takes in incoming data coming in through your depots and then materializes any number of indexes, which in Rama are called partition states, which we usually call P states. And P states are expressed as these arbitrary combinations of data structures, as we discussed. And these data structures they're durable, so they're on disk and they're incrementally replicated. And the data structures can be of any size, including your nested data structures. So that's called subindexing. So you could have a map of subindex maps of subindex sets. And those subindexed structures can be larger than memory, and you can still read and write to them very, very efficiently. Last thing is query, which is how do you actually fetch information from your indexes? And Rama has some really powerful mechanisms for doing that, including reactively. Rama introduces a new capability called fine-grained reactivity, which has never existed before. So you can do things like subscribe to some nested data structure or a piece of a nested data structure, like anywhere within a P state. And then Rama gives you fine-grained information about what's changing. So let's say you're subscribed to like a set deeply nested within. When that set changes, Rama doesn't send the whole set back. It actually sends you a diff telling you, oh, these 2 elements were added and this one element was removed. And Rama provides this capability regardless of the complexity of your data structures. So it's extremely efficient, and it can also power stuff on top of it to do stuff completely incrementally. So I think like in the future, there's going to be some really interesting stuff of building like next generation UI frameworks that can take advantage of fine-grained reactivity to be actually incremental end to end. Look at something like React. React works by doing a diff between kind of the old version and new version of the DOM, which is actually really expensive. And then from there, figure out what's the incremental update to actually apply to the DOM. With Rama, you can actually just make it fully incremental all the way and get rid of that diff.
This sounds like the influence of Spectre a little bit then.
Yeah, Spectre is a big part of Rama. But anyway, that's the programming model of Rama. And when you use Rama, you end up materializing many P states of many different shapes. So when we launched Rama in August, we launched by building a Twitter scale Mastodon instance. Mastodon's like an open source Twitter that's not scalable, can't scale anywhere near Twitter scale. So we built it at scale, end to end, in 10,000 lines of code, which was literally 100x less code than Twitter wrote to build the equivalent at scale. They wrote about 1 million lines of code to build their consumer product at scale. And it was actually more than 40% less code than the official Mastodon backend, which I also thought was interesting because, first of all, our thing is scalable, theirs is not. Also, theirs is written in Ruby, which is generally would be less code than Java. Our Twitter Mastodon instance was in Java using Rama's Java API. So just like a lot less code and just massively scalable. So we ran it, we were actually running it with 100 million bots posting 3,500 times per second at 403 average fan out, which is, I think it was in 1.4 million timeline writes per second at those numbers. So it was legitimately running at Twitter scale and it was publicly available for anyone to use. But that Mastodon instance materialized, I think, something like 80 P states in total across all the different features. Products like that is actually like 50 use cases in one that are very different from each other. The way timelines work is completely different than the way the social graph works, which is completely different than the way personalized follow suggestions works, which is completely different than the way search works. And all that stuff we built on top of Rama, single platform, and all that is open source and just a really good demonstration that this platform can build an application with very diverse needs end to end.
One of the things that helps me to understand technology is to frame it in relation to other things that exist. And the technology that comes up in my mind the most is like Erlang and the Beam, which have some of these properties you're describing, but it's much more focused on messaging and the actors model. And it isn't focused on data transformation. But yeah, do you have your favorite go-to comparisons to Anchor where you see Rama currently and in the future?
Yeah, most people like to reason by analogy, which is actually tricky with Rama because it's really different than anything that's preceded it. Like Rama is a true paradigm shift. It's a major paradigm shift in how you think about constructing applications. I guess one way you could think about Rama is as a combination of stream processor and databases. But that's also not a good way to think about it because databases are so much more limited compared to what Rama can do for that aspect of it. And that doesn't include a lot of the other stuff that Rama is doing with like fine-grained reactivity and what you can do on the query side. But I guess that's in terms of comparing to existing technologies, it's if a stream processor had database capabilities built into it. Yeah.
I was reminded that when you were talking about Rama and some of the influences, is the sense that databases are really these pre-composed solutions that you're landed with. And it's like Lego, where every Lego piece has been glued together with super glue and you're not allowed to unpick it. And there has been, I think, some other influences on us. I think it'd be Martin Kleppmann and the idea of unbundling a database. And so there have been other people who've been thinking, hey, well, let's try and break up a database and find out what actually is it. And there is for example, we talk about unbundling the transaction log, rather than transaction log being this very deeply nested, private part of a database that you never get to see, to actually say, hey, we're just going to expose that. And then once you do that, you can start composing other things like listening and subscribing on that transaction log. And so instead of being locked into pre-composed solutions, which means, for example, in databases, you have a lot of people using this thing called listening on change data control. They're listening on change data sets. So that's the only route in. They have to sniff and put a stethoscope up to the database and find out and listen to what it's doing. And in a very, and all these things are suboptimal and they all have impedance mismatches. And so sometimes you just have to go the long road of breaking up the problem into smaller pieces and then recomposing them. And that feels like a kind of a design technique from the school of Rich Hickey, in a way of just taking an existing pre-composed set architecture and saying, actually, are these the fundamental units, or are there some things more fundamental here?
Yeah. The idea of unbundling the database, making the transaction log explicit, it's basically event sourcing, right? That's been an idea for a long time. And sort of that was, and that effectively is one of the pieces of Rama's program model, right? Is the data portion is event sourcing. And Rama's depots are essentially event sourcing. It essentially is that transaction log. That is the core data coming in, which may have multiple impacts on multiple views of your data. Like essentially Rama is event sourcing plus materialized views. Both of these concepts have existed for a very long time, but it's doing it in a generalized way and also integrated way, such that it's able to avoid the impedance mismatches, which have plagued backend development for many decades.
Yeah, you talk also, I think also the fact that with Rama, the ETL layer is something that is in your control as a programmer. Sometimes in your domain, you have things, you mentioned Twitter, the nature of following is that you want to decide what is the data affinity, where should that best for performance reasons. I might need to make decisions that actually are going to affect things very deep down in the architecture. And in the traditional approach, we layer everything. And so we don't allow people, programmers certainly in their own domains, to influence what happens at lower layers. It's closed off to you. And so difficulty in design is how do you break something up but still allow developers at the top of a stack still to have control and influence and control, just to be able to go right down deep into the stack. And that's where the huge cost explosions happen when you don't have that control, because you're dealing with other people's assumptions, which are wrong in your domain, but there's nothing you can do about them.
Yes, exactly right. Yeah, those are impedance mismatches, and they're brutal. And actually, the moment you choose to use a database, which isn't actually a choice, you don't really have a choice in that regard, but the moment you choose to use a database, you have brought a major impedance mismatch at the very core of your architecture. And that bubbles up cost everywhere. And yeah, like, this is why it took me 10 years to go from the vague outline of what Rama could be to it actually being working, because it was a struggle to figure out what are those abstractions? Like, what control do you need to give, and how do you give that control? Basically, like, my process for design is to I basically just resist building anything, especially an abstraction, as long as possible until I cannot take it anymore. That is, it needs to be that, like, and I actually wrote a blog post about this a long time ago where I called it suffering-oriented programming. But before you do anything, you better be suffering, because you don't have it, like really suffering. Like, it should be driving you crazy. And with Rama, I basically just went through that iteration over and over. So like, I knew p-states as data structures. I knew that a data flow API of some sort would be what you want to use to program it. Initially, I just thought the data flow API would be like DSL, like catalog, right? Like specific to the domain. And basically what I would do is I would take like all the use cases I'd ever worked on at Twitter, previous startups I'd worked on, as well as everyone I'd ever helped with. And this huge list of diverse use cases. I'd have an idea for how to express it, and I would try to just play with it with pseudocode and see how does it play out. And just iterate, sometimes spending weeks or even months just trying things out, seeing what it looks like. And over a very long period of time, I went from this notion of like data flow being this like narrow thing to it needing to be a general purpose programming language of its own. And it actually ended up being legitimately a new programming paradigm. Yeah, which we actually just 2 days ago, we released the Clojure API, where we actually have released that programming paradigm for everyone to use. And it's really interesting, the programming paradigm, because through this process of resisting making an abstraction, I eventually reached the point where I realized I needed something more general than a function, right? Functions have been the basis of programming languages forever, for basically every programming language except for maybe logic languages, which are their own thing, right? The paradigm of a function is call and response. Call a function, it does some work, and the last thing it does is it returns you a result back. And so what I discovered with data flow, I needed another primitive, which is based on a different paradigm, which is call and emit. So you call an operation, and then it emits values to downstream, to whoever is interested in information downstream. And it can emit one time, or it can emit many times. It can even emit 0 times, right? And also it can do work after it emits or in between emitting. And then from that, I realized I actually want to emit to multiple targets, to multiple output streams, right? And that's essentially what data flow is, right? You have an operation, you have different streams that can come out of the operation, and then you have other code attached to that, to those different streams, right? So I call this generalization of a function a fragment, where it's based on call and emit rather than call and response. And a function is just a specific kind of fragment where it emits exactly one time, it emits exactly one field, it emits to exactly one stream, and that's the very last thing it does. It can't do any work after emitting. So a fragment's actually a pretty big generalization of a function. And that was one of my very early breakthroughs when I discovered this programming paradigm, built the language around it, which, credit to Clojure, that you can build an entirely different programming paradigm, essentially a different language within Clojure, It's still Clojure, but it's also a different language. And it also interoperates with Clojure. I don't think you can do that in any other language. And that was my big breakthrough for figuring out a major part of the computation piece, or how do you express these highly scalable distributed computations in an elegant way and also general purpose way. And it turned out that I needed a new program paradigm, and it needed to be Turing complete and general purpose. So that was a big breakthrough for me.
I think the thing in terms of requirement specifications, I think the thing that jumps out at me here is that over time, and this is maybe a hot take, so apologies for this one. But over time, as an industry, we've moved towards requirement specifications that are based on what the languages can do. And I get the feeling with this that this is going the other way around. This is moving the programming language to being more in terms of how you would naturally specify what, as you say, Nathan, what a system like Twitter does. When you're naturally describing what a system like Twitter does, you're describing it in terms of this data goes from here and this person does this, and then when this person does this, I'd like the data to flow this way.
Well, naturally, like, you're always going to be limited by what your tools let you do, right? So you have to specify it. If you're building a product, you're restricted by what your tools let you do. But if you want to innovate, then you can't think like that. You have to think more fundamentally. So that's going back to thinking from first principles rather than thinking by analogy. If you're just thinking in terms of what people have been doing for the past 40 years, you're never going to do something fundamentally different, right? Which is why it was so important for Rama. Like, never in a million years would anyone ever get to Rama by just thinking by analogy in terms of existing systems, because it required deconstructing it into the first principles, deconstructing the idea of a database and the data structures, and so on. And then that's how you get to these. Rama reduces the cost by 100x, multiple orders of magnitude, for building applications at scale. And the only way to get to that is to start from first principles, throw away all your assumptions, and just let the first principles take you where they do. And that took 10 years.
It's about taking that time, isn't it? Taking that time to step back and think about it, which is
Yeah.
quite a precious thing in our industry, I suspect.
I think it is. I've been struck by how much of development today, unfortunately, is very time boxed into very short iterations where there just isn't time to think. You've got time to cut the feature as fast as you can. It probably has to be the first thing you think of. And there isn't many kind of commercial environments where, apart from, I suppose, academia and research institutes, but even in those places, the pressure to deliver the paper or to get onto the next thing. So actually carving up the space to really take time to think hard and without a deadline, without saying, Nathan, you've got 5 weeks to come up with the next abstraction. And that's not about, when you're talking about suffering, squeezing every single last thing about what you currently have until you're ready to commit to that abstraction. That isn't something that you can apply a series of deadlines to. And so I think we're very fortunate and privileged if we do get an opportunity in life, but very few people do. But I just wonder what the industry would look like if we gave a bit more space to people and younger developers to take time to think and to take time to go on journeys of discovery as you have.
Yeah, I was fortunate to be in a position where I could do that. Like, I was, through the Backtype acquisition, I had the financial freedom to be able to do something like this and commit to it. I didn't know it would take 10 years when I started. I knew it would take a while. I didn't really know how long it would take, but I knew it was important. So that's why I committed to it. It was the opportunity I saw back in 2013 when I started working on this was a chance to advance human potential fundamentally by just reducing the cost so much and just the impact that's going to have, right? Enabling small companies to do what currently requires big companies, massively increasing innovation, massively increasing the speed at which people can iterate, and also just increasing capability by just making things possible which are currently are too expensive. So that was very motivating to me. That's basically what kept me going over the 10 years.
I think that there are some opportunities to, even when you're in a job, to take half an hour out of your day, sometimes even if it's just 20 minutes, and to have a side project or to have a thing that you're thinking about, which is not constrained to a deadline that you've got to come up with something into a 2-week period of time, but just to be able to have those little projects that you can have and you can just keep thinking about. And as you're walking your dog, or you're walking up the beach, or anything there's a lot of things in life, that commuting and things like that, where actually there is some space and time to just think and the question things, to question what is the, I love when you say 100x, because that really resonates with me. And we said this on the podcast many times, that there are many people who think that we're almost at the tail end of the industry, that we've invented everything and it's all done now and it's just a bit of configuration around the edges. And then there are some of us who believe we're just at the very beginning of the industry, and there are still 10x and 100x opportunities. We're not talking about percentage optimization of making a business process 2% more efficient. You're talking about 10,000 times more efficient. And that's tremendously exciting to know that there are still opportunities for improvement that large.
I'm sure right before cars were invented, people thought that horse and buggies, they had completely optimized it. They had made travel as good as it was ever going to be.
Exactly.
Well, there was that patent office quote, wasn't there, at the start of the 19th century, saying we might as well shut down the patent office because everything's been invented now.
Yeah.
So
20th, maybe. Sorry.
The developer productivity seems to be the headline thing, right? But clearly, when you've been developing Rama itself, like you've been a small team, fairly short time period. We know from our own experiences building like a storage engine is hard. But like in this day and age where you have high level tools, you have the JVM, you have Clojure, you can assemble things quickly, and your replication and fault tolerance is presumably built. You've had to build some internal tooling to support. I was just wondering if you wanted to lift up the hood of Rama a little bit, tell us about what's inside and what that experience has been like building a system like that.
So there's so many aspects to it. So I'll talk about two that are interesting. So P states are really interesting, right? Expressing these durable indexes, data structures of arbitrary size composed arbitrarily. So we're actually using RocksDB under the hood for the actual durability part, with a lot of abstraction on top of that to implement, especially to implement sub-indexing, which allows these nested data structures to be of arbitrary size. Turns out you can implement these data on top of an LSM tree like RocksDB. You can do that. So Rama integrates computation and storage, right? So actually there's two ways to do ETLs in Rama, right? These functions that consume data coming from depots and materializing your indexes, which are your P states. So there's streaming and there's microbatching. Streaming has 1 to 2 millisecond update latency, and it provides either at least once or at most once processing guarantees. You can configure that. Microbatching is like minimum 200 to 300 millisecond update latency. It's even higher throughput than streaming. Both of them are scalable, but microbatching is higher throughput and actually provides exactly once semantics. And actually, the way specifically that we use P states and RocksDB under the hood from microbatching and streaming is actually different to achieve these to just achieve the properties that they have. A lot of what happens under the hood to achieve like high throughput is a lot of batching. We call it dynamic auto batching, where basically like it's much more efficient on RocksDB or any disk operation to write multiple things in batch before you sync the disk, right? And so a lot of the stuff internally and how these things work is you have a queue of work and you execute whatever's up on your queue up to a limit. And then you combine all the writes they're doing into a single disk operation, right? And then you provide the fault tolerance at the level of the batch. So if anything fails there, you end up retrying the batch. Now, when you retry a batch in microbatching, it's transparent such that it's like nothing ever failed at all. You get exactly the updates to your P states are as if nothing ever failed, even if it failed many times. Whereas streaming, you might have at least once semantics. And so the way that works internally is different from microbatching and streaming. The way the exactly once thing happens is that we actually store as part of the partition information about our progression into the depots that we're consuming from, which you can only do in microbatching and not in streaming just because of just the nature of microbatching. Executing as basically the way microbatching works is that you process all the data that's accumulated since the last time during the last iteration as one batch of data in one microbatch, right? And you don't start the next iteration until the current one finishes. And so with that, we're actually just able to store the partition information with the partition. And that way, if we have to retry the microbatch, we can start from the previous version rather than keep writing to the existing version as you have to do with streaming. So that broadly is how P states work. Replication, which was by far the most difficult thing to build, so provides this very strong guarantee. Any information that becomes visible on a leader will be visible on all future leaders. So the basic way replication works, I'll try to explain it in a way such that we don't need diagrams. So I'm going to have to stay pretty high level. So the basic mechanism powering replication is this thing called a rep log, which is a replication log. And so whenever you do any sort of operation that needs to be replicated, like you're writing to a P state or writing to a depot, and there's also various internal things Rama is doing that needs to be replicated, you first write it to the rep log. And that rep log, you have many different kinds of rep log entries. One might be a streaming P state update. Another one might be a microbatch P state update. Another one might be a microbatch commit. Another one might be writing progress information about ETLs, like internally. And so the key thing is that it's an ordered log, right? And so when you create the rep log entry, it doesn't do anything, right? All it does is add to the rep log, and it doesn't get applied to your objects, to your P states, depots, or other internal objects until the replication system has applied that rep log entry, right? And we don't apply it until it's been sufficiently replicated. So the idea is that you write to the rep log, and then the leader forwards entries to followers. And then once the followers have confirmed receipt of those entries, then the leader can apply it, as well as letting the followers know that they're free to apply it. That's this concept of an apply offset. So that's the broad mechanism. And then to deal with stuff like failure, you have this concept of min ISR. ISR means in sync replica set. And so you might have, let's say, replication factor of 3, which means there's 3 replicas for every partition. You might have a min ISR of 2. And so when a leader goes to apply an entry, it's waiting for at least 2 replicas including itself, to acknowledge receipt of that entry. And if a certain amount of time passes, which is by default 2.5 seconds, and you haven't gotten receipt of that entry from that last replica, then before you apply the entry, you kick that replica out of the ISR. So that basically makes that replica ineligible for becoming a leader. It makes it impossible for it to become a leader in the future. So now by the time you apply, you're guaranteed that it's on any future leader, which is your min ISR set. If you can't reach min ISR, then you can't apply and you're stalled until stuff has caught up or come back up. Because that's ultimately that is the guarantee, right? The user says, if I'm going to make anything visible, I need to have a certain guarantee of replication. So that's the basic model of replication, right? Which is actually similar to like how a system like Kafka works. Now, on top of that, you have to deal with, what do you do with replicas that are not in the ISR, where they have to catch up, right? There's actually 2 cases for that. One would be a follower is pretty close, right? So the way the rep log works, you don't store the full rep log forever. That would just be using a prohibitive amount of disk space. So we store at most 20,000 entries of the rep log. So if a follower is still in range of the rep log, like its last rep log entry is still within that 20,000, then it does what's called near horizon catch up, which is actually the same as regular replication, where the leader forwards it entries in batches and the follower progressively backs up until it's in range. The leader detects, oh, it's now within range. I can now put it back in the ISR when it eventually catches up. Now, the harder case is, what if it's not in range of the rep log? In which case, the follower cannot reconstruct the state that it needs based on the rep log. So that is called far horizon catch up. And so in that case, the follower needs to transfer all the data for all objects, all P states and depots for that partition from scratch. And it does that over multiple transfer rounds, right? So the first transfer round is going to be really big. You might be transferring hundreds of gigabytes of data, right? And then you just keep on doing transfer rounds until you get within range of the rep log, right? Such that I've done a transfer round. I know that this transfer round was at least starting from rep log offset 1, 2, 3, 4, 5, 6, or whatever. And then I'm within range. The leader still has that rep log entry from there. So I can start applying rep log entries from there. For far horizon to work, rep log entry application needs to be item potent, right? Because as you're transferring data, like the leader's still writing, so you're going to end up transferring data potentially according to different rep log offsets for different objects. And you just know the min offset where you need to start from. So that might be redundant with what you've already transferred. This whole thing only works if the rep log entry application is item potent, which is something we've ensured for all rep log entries. So that very broadly is how replication works. On top of that,
a follower could move in from near horizon into far horizon. If it was falling back, presumably it can fall from a near horizon replica into a far horizon replica.
Yes, and it detects that.
Or is that the point at which it falls out of the ISR and then?
Yeah, that can happen. And then it would have to transition to far horizon.
Right. Yeah.
So then you have stuff like microbatch, and microbatches, they can be really big. You're looking at a minimum latency of 200 to 300 milliseconds for executing a microbatch. But if you, it also depends on what your microbatch is doing. If your microbatches are very intensive, and if you are running at very high load, your microbatches could take 5 seconds, right? In which case, these replog, what you need to replicate all at once is actually a huge amount of data, right? And so if you were to put all of that data onto the replog at once, right, 5 seconds worth of computation, you have now delayed everything else from replicating for much more than their SLAs, which is like 1 millisecond. So to get microbatching to work, it actually breaks up what it needs to replicate into many entries, and it allows other things to run and replicate in between those entries going. And so that's how we achieve fairness with something like microbatching, which is doing something which has very loose latency requirements while still being able to coexist with something like streaming, which is very tight latency requirements. And there's lots of details into like how we make that work. So that broadly is how replication works. And our first version of replication didn't work. It worked on the happy path, didn't work at all on the unhappy path. And it took many iterations and most importantly, a ton of testing. And we became like very just obsessive about testing in order to work out all the kinks of a system like replication. And when you're doing a system like this is true of any distributed system, and it becomes more true the more complex your distributed system gets. And Rama being such a cohesive system, it's basically as difficult as it gets for being able to achieve any of the properties you want to achieve. And the only way you know anything about any system, especially complex systems like distributed systems, is empirically through testing. So that has been probably where we've spent most of our time, honestly, in building Rama, is on testing and just developing ways to test it such that it is testable, which is a huge...
Any novel approaches that you've invented for testing? Any kind of new ideas that you can share?
I think the most important thing we're doing, this is not novel. We actually got inspired by the Foundation DB people. This idea of deterministic simulation. It's actually very unintuitive. The natural way that you would write a unit test for a distributed system would be you just run it like the way it normally runs, right? It's a distributed system, so it runs in parallel across multiple threads. This unfortunately isn't true of all systems, but you should have some sort of like local mode where you can run the whole thing within a single process as opposed to many nodes. And then it's all within the process across multiple threads, but you just run it as is, as it normally runs, right? That would be the usual way you test it. That's how I wrote Storm. And it turns out that there's a much better way to test, which is to actually construct your system such that you can run it in a different execution mode where the whole thing runs on a single thread. You have a controller which chooses for every iteration which entity is allowed to run an event right now, right? So the issue you run into when you're running things in parallel across multiple threads is that you can't reproduce errors, right? So you're running a test and there's some freak confluence of timings and event orderings such that there's an assertion error, right? And then you go and you run it 1,000 times and you can reproduce it maybe once in 1,000 times, right? But reproducing it doesn't help you because it doesn't actually tell you what happened, right? So then you add some logging so you can try to trace what happened, right? But your logging actually changes the timing. So maybe now instead of reproducing once every 1,000 times, it reproduces once every 10,000 times. Oh, and every run takes 20 seconds, right? Or maybe it just never reproduces again, right? So you can't actually debug things. It's like ridiculously expensive to track things down. And sometimes it could be impossible, right? So deterministic simulation, like at first you might be like, well, that's not a good way to test things because things aren't concurrent anymore, right? So what about concurrency bugs, right? And that's true. Deterministic simulation will not track concurrency bugs. But the way you do, the main observation there actually is that most bugs in distributed systems are not concurrency bugs. They're bugs that have to do with time and order. And that's what deterministic simulation excels at finding. And the way deterministic simulation works is that you basically, before you start your run, you choose a random seed, right? You print that seed with the run, and then you use that random seed to inform all decisions, right? That informs who's the next entity that gets to run an event, right? And then you can, if you have a failure, you just plug in that random seed, you run it again, and then it reproduces exactly because it's an identical run, right?
It's like a sort of procedural generator for a game or something. You're going to create a
Exactly.
run that is a sort of an alien world that it's all come from one seed,
Exactly.
and so that you can go straight back to that alien world
Exactly.
where you had the bug.
Yeah.
And
And
an
it,
event in this case is like a read to state, a read from state, a write to state, or like a message passed between two
yeah,
processes.
this task thread on this worker gets to run one event, and that one event could be an ETL event, could be a p-state read event, it could be a depot append, anything, right? As well as the million internal events that we have, telemetry collection and system events and transition events and all sorts of, there's tons of them. That's the general approach. Actually making that a reality is hard because things need to be deterministic. Some of the stuff that's bit us in the past that we had to track down would be like, if you're iterating on a hash map, that will not be deterministic, right? So if you actually want to make that deterministic, you have to implement on the keys in sorted order.
Yeah.
Stuff like that, right? There's actually many reasons why something might not be deterministic. And you need to make sure you make it deterministic in a way that doesn't cause performance regressions in production, right?
Mm-hmm.
That was a challenge. And it took us a while actually to get it like fully deterministic in all cases. But now with a system like this, now when you have a failure, you can add as much logging as you want because the logging is not going to change the order of events, and you can very quickly track down what went wrong because you can reproduce it every time, and you can just keep on adding more logging or more information to track it down. And so you have this like crazy rare error that happens with like weird timings and event orderings, and you can track it down. Oh yeah, another thing you have to do with this is actually abstract the concept of time. So time advancement has to be explicit for this. And there's all sorts of strategies for doing that. And some of the cool things to do to determinist simulation. So first of all, every time you run it, you're basically creating a new random exploration of the space of possible orderings of events, right? But you can do other stuff. You can influence that and actually say, I actually want to starve this entity of any events for a while and then let it come back in later and let's see what happens, right? Let's actually force like these really weird orderings of events and make sure stuff still recovers. That could cause many failures, but it should still recover, right? Some of our determinist simulation tests range from unit test things of let's test one very specific scenario. And then another one of the really interesting kind of tests we write, these are like a chaos test where it's like uncoordinated, where we create entities which are going to be uncoordinated. They're going to append data to the Rama modules, and then they're going to do a bunch of reads, or they'll do those intermixed. And they're just running on their own. And then we have the modules running, doing something else. And then we have something else running, which is randomly killing processes or creating partitions or doing other sorts of disturbances.
When you say random, you mean random according to the seed?
Yes, exactly. Always have to be using a random number generator, which is based on a derivation of that seed. And so it's a very uncoordinated test. And then you assert on very high level properties of no data loss, no assertion errors, or if we see errors, we only see errors of this type and so on, right? And those tests are really interesting because you can actually explore with one test just a huge number of possible interactions and race conditions, because eventually some seed is going to explore that, right? And that has helped us track down a ton of things. Okay, so that's one major piece of how we test. And actually, determinist simulation is so profoundly game-changing for the development of especially distributed systems. I would actually say you should not trust any piece of infrastructure, any distributed system that is not using determinist simulation as part of its testing strategy. Because if it's not using determinist simulation, it is going to be full of bugs, period. Because it's not able to explore it's not even able to explore those parts of the space of possible event orderings, which eventually will happen in production. That's how game changing it is. But it's also, that can't be your only testing strategy, because first of all, you're running in a different execution mode than production, and it's not testing true concurrency, which you still need to test.
And you've got to discover the failure modes, and you've got to discover the kind of circumstances that happen in the real world and be able to simulate those and discover them. And discovery is just part of it.
Correct. Yeah. And some of that stuff may not be possible to simulate, especially because you're not running a real cluster. It's still all within one process, right? And so the other end of the spectrum is what we call quality testing. So we basically have, I think we have 50 nodes on AWS right now, where we have multiple Rama clusters deployed, and we are constantly hammering those clusters So they are processing a lot of data. We're just like generating random data. We have all sorts of models deployed there. And then we're randomly doing what we call disturbances to those clusters. So disturbances range from kill one worker to kill multiple workers to kill actually every process on the cluster at the same time, do a full cluster restart. Another disturbance is like a network restart, a network partition, right? Let's make sure that it is able to deal with that appropriately. Another disturbance would be to suspend a process for a while and actually force it to go into far horizon, right? And then we combine that with worker kills as well. And then we have one cluster which is dedicated to just like one module running for a really long time. We have another cluster that's dedicated to testing module transitions. So one of the core things that Rama provides is module update, which is when you have an existing module and you want to update it with new code, new features, new P states, new topologies, whatever. And so we have one cluster dedicated to doing module update and also doing disturbances during module update. It turns out those transition periods for a module were quality testing revealed a lot of issues with that, which we had to make, which led to us making it fault tolerant and actually led to us making simulation tests to replicate those things that we found in production, right?
One graph that just when I was reading the initial Rama announcements and the Mastodon clone that you built, and then you had this graph that showed this kind of it was this linear scalability all the way up, and there was this plot of Twitter is here 2/3 up, and you turned up all the levels to test it even beyond Twitter scale. For many of us, Twitter is this huge thing. I have no idea how it works. We know it has huge scale, and to be able to show that was I thought just incredible. It blew me away. And I just thought, wow, I've got to take this thing seriously. You must have been very pleased with when those benchmarks finally came out. I don't know the story, how hard it was to get to them, but to actually be where you are today must feel very gratifying.
That scalability graph, it's so simple. It's just a straight line. It was so much work to get to that point. So actually, when I was first doing that testing, this was actually before Mastodon. So we were doing we had like other like test applications before that. And the first time I ran it at scale, it actually wasn't scaling linearly. It was scaling like very sublinearly. And it turned out there were scalability issues in the Rama implementation with microbatching specifically. And it actually required like major innovation to make it scalable. This was the problem of detecting completion of processing of distributed computation. And yeah, it turns out the way to do that at microbatching to make it scalable is very different than how you do it with streaming. Before I was using the same algorithm as stream for microbatching, which because microbatching essentially coordinated was not scalable. But then once I solved that and saw that linear graph, as well as just everything that went into building the rest of Rama, yeah, that was one of those like great moments of just, I have achieved that vision of what I initially was seeking to do in 2013.
Yeah. And you like the fact that it took you 10 years, but to actually come out of that and to go into an announcement phase as you are now. This week you've announced, something we're very excited about, of course, the Clojure API, the native API to Rama, which I think is certainly going to be interesting to the Clojure community. But much more beyond that, the Java community is huge. I was going to ask a question about it, introducing Rama into an existing infrastructure. At Jux, most of our clients are finance, fintech clients, where two things are important. Adding up numbers and guarantees are important in fintech, and also scale, because some of our investment banking clients have vast scale. The number of trades, the number of risk numbers that kind of flow through these systems is vast, and all the problems that you talked about millions and millions of pounds of waste going into developing systems and creating new databases, and the vast, all the problems that the industry faces to do with complexity is found in banking. If you're at a bank, how would you suggest introducing Rama to one of those kind of organizations that have a mature?
Yeah, a lot of people get there's a misconception that Rama is like an all or nothing tool because it's able to do your entire backend end to end. That could not be further from the truth. So Rama is very easy actually to integrate it with other tooling, just like everyone's been doing for decades with existing tooling. So we actually put a lot of effort into making sure Rama has a very simple but comprehensive integration API. So if you want to interact with a database from Rama, very easy to do. You want to interact with the REST API from Rama, very easy to do. You can just use that directly from the code that you're programming in Rama. And likewise, Rama can consume data from data sources other than its internal depots, right? We actually open sourced this project, Rama Kafka, so that Rama can just consume data directly from a Kafka cluster, and there's no difference in functionality compared to consuming from a depot, right?
Right.
And that's very important, right? Because in practice, like no one's going to just replace everything that they built over potentially many years on day one, right? It's just not practical, right?
Mm-hmm.
So the way to introduce Rama to an architecture would be, all right, you have this new feature you want to build, right? And so to learn Rama and to start to understand its capabilities, you can use Rama just for that, and then use the integration API so that you can interact with the other things that you need to interact with. Maybe you have an existing Kafka cluster you want Rama to consume data from, and maybe as part of the processing for this, you need to query your Cassandra database, and you also need to query your Elasticsearch database, or you also need to write to those databases, right? And then maybe for some of your new stuff, you'll use Rama's P states, and you'll do computation, different kinds of computation on top of Rama. So that would be the way to introduce Rama into an existing architecture. And then once you learn it, it'll become very apparent just how much faster it is to build with Rama. And then more importantly, how much simpler it is. And then from there, you can look at, okay, we can save so much cost on our existing systems that are so complex. So you can start to migrate those piecemeal into Rama. And then the more you have him running within Rama, the simpler things get. Because now everything's under one cohesive model, one integrated model, and you can benefit from that.
So what are your future plans for Rama? You're out the door now. You've gone public. What does the future hold?
Yeah, so right now we're in private beta. We have a build of Rama that's publicly available, but you can't use it to run a real cluster, but you can use it to develop Rama applications. As I alluded to, it has this thing in it called in-process cluster, which simulates a Rama cluster in process. So you're actually able to use Rama fully in this environment to explore its capabilities or even just develop your full application. When we were developing Mastodon, we actually just developed the whole thing on top of IPC, and it was like 3 months of work on Mastodon before we ran it on a real cluster, right? But to actually get access to a full cluster, you'd have to be part of our private beta. And that's like our main focus, which is working with our private beta users across very diverse domains. Our private beta users are all over the place right now, like very different use cases, very different domain models, and so on. And then just helping them achieve massive success. So that's the main thing we're focused on. And those, our private beta users will just be, I guess, more data points, right? Just showing that Rama can be applied all over the map, right? To very diverse use cases, right? So besides our Mastodon example, we're going to have many examples from all of our private beta users. Mm-hmm. On the technical front, there's a few projects we're working on right now, which we're looking to get released relatively soon. So one project we're working on is backups, which is back up the full cluster state to a kind of anywhere that you want to back it up, right? Whether it's another data center or something like S3 on AWS, right? And we're actually going to ship that with an S3 backup provider, like open source and out of the box. So that's obviously a very important thing to have for running stuff in production. And so we're aiming to have that ready within 2 to 3 months. And it's incremental backups. So like you could run it every half an hour, and basically it just uploads the data that is different from the last time it uploaded. That makes sense. Along with a manifest of what's like the total set of files you need to reconstruct the various objects and reconstruct the modules. Another thing that we just started working on, I don't have an ETA for this because we just started working on it, but it's going to be an open source library called Rama Search, which is basically like, it's going to be like Elasticsearch, but as a library. And so all the capabilities of search, but as a library that would just be utilizing the expressivity of P states and ETLs and the query things you can do with Rama, but as a library, right? So you're actually indexing your documents directly instead of having to convert it to something like JSON, like you have to do Elasticsearch, and then you get a lot of benefits from the integration. So that's early stages. Search is actually like a huge, expansive space. So we're not going to be doing the full feature set of Elasticsearch for the first release, but we're just going to focus probably on like single term search and multi-term search, all the stuff that goes into that for the first release, and make sure our performance is comparable to Elasticsearch.
That's so exciting that you can almost say, hey, you want search, that just becomes a plugin or a library or just addition, because you've got the underlying fundamentals. So you just compose in different ways. You can bring in an ETL, you can bring in a search algorithm, a min-max, or some of the kind of algorithms that are super useful for search.
And even more importantly, it's a library, not a system, right?
Yeah.
So it's something that becomes part of the modules you're developing. You could make it its own module, but it's even more interesting when it becomes part of your existing module and just integrates with whatever other random data processing and stuff that you need to do.
Yeah, there's echoes with Lisp or Clojure where things like becomes a library. Communicating sequential processes is a library. You want logic programming, you bolt on a library. And if you have that capability in the language, then why everything is snapped on. You don't have to build an entirely different system. And with all of the impedance mismatches that entails. I think we're kind of out of time, Nathan, and I want to wrap up, but just wanted to say, thank you for your time on this show. I think projects like Rama are just fantastic inspirations for people who want to go on these long journeys and to just see what you've been able to do in 10 years with nothing but thought and hard work, and that you can achieve great things. And I think that's a kind of a wonderful message. What I learned in my career is that tools are important, but then if you're willing to put in the hard work and the thought and the persistence and the dedication, you can achieve great things. And I think you're a shining example of that. And thank you.
Yeah, thank you. That was fun talking to you guys.
Yeah, thanks very much.